the shuttle. So for instance, that it can perform parking maneuver, it can guarantee some anti-collision protocol, and it respects the traffic. And the idea is you want to model everything in mathematics. So the model of the system will be a game because it has to interact with its environment. The games we will consider are concurrent game structures. So you have a graph, you have a starting point, and you have multiple players, and each player will choose an action. So for instance, you can have a shuttle and a car, and the shuttle will choose to go right, and the car will choose to go left, and this tells you which transition in the graph you take. And so you can have all sorts of possible action profile. We call it an action profile when each player has chosen an action. And then you take the following transition. And for instance, if the shuttle and the car choose both right, we will go to the position P2 in my example. And then from this position, we rinse and repeat, and each player chooses an action, and then we follow the transition. And thanks to that, we define a play. So a play is a sequence of action in the graph, or a sequence of position, that can be transitioned in between 2 by 2. And the winning condition of the concurrent game structure is given by a set of play. And because we have possibly more than 2 players, the idea is that we gather players in coalitions. So we will have one coalition that wants the play to be part of a given set of plays. That is the winning condition. And the anti-coalition that wants the play to not be within the set of winning plays. That's all. Usually, and for the rest of the talk, this set of winning plays is given by an LTL formula on some property that are labeled on the positions of the structure. And in order to formalize our requirements, we will use strategic reasoning because we want to manipulate the behaviors of each participant, of each player. So the logic we will use is strategic logic. So I will first present with strategy logic. So strategy logic is a logic where you can quantify over strategies. This is the point of the logic, and you can tell things like that. So for every strategy of the car, there is this strategy of the shuttle. Those are basic quantifier, and then you need to give each strategy to a player. So you will say the car performs the strategy of the car, and the shuttle performs the strategy of the shuttle. This is what we call a binding, and it is really a core element of the logic. And on this example, it looks like it is obvious because, of course, the car will play the strategy of the car and the shuttle the strategy of the shuttle, but we will see that it is really interesting sometimes. And then you have an LTL formula that is globally, if the car and the shuttle crash, it means it's not the fault of the shuttle. This is just some abstract LTL goal for us, and this tells you that it's not because of the shuttle that there was a crash, because sometimes you can't avoid the crash. So I don't want to spend too much time on the LTL part. Just consider this as a winning condition, okay? And this kind of formula where you have first quantifiers, then a binding, and then an LTL formula is what we call a one-goal formula. And it's a specific subpart of the logic that is really relevant for the rest of the talk, and it's also the first thing you can think about when thinking about strategic reasoning and requirement. It's simple. Is there a winning strategy in some game? We can think of another one for the traffic protocol where it looks kind of the same, just the goal change. And the point is that maybe we want the strategy of the shuttle to follow both the anti-collision guarantee formula and the traffic protocol formula. The problem is that here we just check whether there exists one that satisfies the anti-collision formula, and if there is one that satisfies the traffic protocol formula. But we want to have both. We want to have one strategy for the shuttle that satisfies both formula, and it's there that the binding can shine, because we can make this formula in the logic, strategy logic, where we quantify twice on the strategy of the car, but only once on the strategy of the shuttle. And what we do is we say, if the car plays the first strategy, then the shuttle must satisfy the anti-collision guarantee. And if the car plays the second strategy, then the shuttle must satisfy the traffic protocol formula. And so you see that it's the same strategy for the shuttle that has to react to different strategy for the car. And this is the point of strategy logic. Unfortunately, there is a problem with this view. It's a problem about dependencies of the quantifiers. So just to enter a little bit in the details, a strategy usually is defined as a map from histories to actions. So an history is just a finite play in a way, and it tells you, once you have your finite play, what is the next action you have to choose. And because of that, it can be seen as a tree. Okay, you have the tree of all the possible histories, and at each point, it is decorated with which action you should take. And you can think of each strategy that is quantified as a tree. But because of the order of quantification, in the strategy for the shuttle, the action you choose after a history, the red history that is presented, will depend on the whole strategy for the two car, the two strategy for the car. And in practice, we don't have the strategy at hand. And this is what we call a non-realizable strategy, because even if the strategy has the good form, you cannot compute it because you need extra information, so you have extra dependence on your strategy. And we want to prevent that, because the point is to be able to extract the behavior of the shuttle. And so we want the strategy, the action chosen, to depend only on what happened along the current path, so along the current history. This is really close to the notion of behavioral strategy that is discussed already in the literature. And we will compare ourselves to the timeline semantics, because timeline semantics exactly respond to this problem. So it's a new semantics for strategy logic that, instead of just taking the quantifiers as first order quantifiers over strategies, is defined through a Skolem map. So it's almost a Skolem function that enforces realizability inside the definition. The problem is that it's not compositional and it's a bit ad hoc. And here in this presentation, I will discuss a new approach to solve this problem. So the approach is to define a game theoretic semantics. What is a game theoretic semantics? It's when you take a formula from your logic and a model, so for us a game, and you define a game. So the idea is that we will define a new CGS, so concurrent game structure, and so that the game is won by one player if and only if the formula is true on the model. And so us, because we have a logic about games already. We will just translate everything, but inside the one goal formula. So in a way, it's a reduction from multiple goal to one goal. And we will say that the game satisfies in a realizable manner the formula if and only if the construction of the game, the new game, satisfies the construction of the new formula. And why one goal is really interesting, because we already know that in strategy logic, if we have a one goal formula, we can restrict ourselves to realizable strategies. And this is given for free by this paper. Okay. How do we build the game? The idea is we take the first game, we take the first formula. So I have taken the same formula as before, where we have our two goals for anti-collision guarantee and traffic protocol. And what we focus on are the bindings. And we put ourselves in the initial position of the game, but we decorate this position with the current bindings. So for our example, we only have two. I will, yes, I have to mention that this construction is effective for the conjunctive goal and the disjunctive goal fragments. So when we have only conjunctions of binding LTL formula or disjunction of binding LTL formula. I will discuss that a little bit later. And so from the first position, what we do is that now, instead of the player choosing an action, it's the strategies that choose an action. So in a way, the new player of the games are the strategies. They all choose an action, and thanks to the bindings, we can compute what would have been the action profile in the original games. So in this example, we get this action profile, and now we can look at the transition in the original game to know where we go in the new game. So here we have left-right for anti-collision protocol, and we see that we should go to P2. And for traffic protocol, we have also P2 because left-left also goes to P2. It's the same position, so everyone goes to P2. It's easy. Now, if the strategies don't choose the same transition, this can be a little bit problematic because, for instance, here we have the binding anti-collision that goes to P3 with right-right, and the traffic protocol that goes to P1 with right-left. It's not easy to know where we want to go. Do we want to go to P3 following the anti-collision binding, or to P1 following the traffic protocol binding? We can't decide, and we don't want to introduce non-determinacy in the model. So what we do is we add a player that is a special player for the Boolean connectors. And this is what we meant by giving a game theoretic interpretation of Boolean connectors. It's because the Boolean connectors becomes a player in the game, really literally. And this player will choose which binding we take. And this player will be part of the coalition if it's an OR, if it's a disjunction. But in that case, because it's an AND, the player is antagonistic. And that's all. This completely defines the new game. And what we have is we can translate the formula to represent what would have been the goal, but in this new game. So we have the new formula is just the same quantifier prefix with the addition of the quantifier for the new added Boolean connector. That is universal because it's an AND, but it would have been existential if it's an OR. The identity binding that just maps each strategy to itself. And then an adaptation of the LTL formulas saying just if we always follow the binding for one goal, then we must satisfy the formula, the LTL formula of this goal. And that's it. Those are not really binding, it's just the property. Do we follow this binding in the game? It can be encoded easily with the labels. And what we have shown is that the new constructed game satisfies the new constructed formula if and only if the game satisfies in a timeline semantics way the formula, the original formula. And so it means that we have captured exactly the behavior of this timeline semantics that has a Scholem-like definition and that is ad hoc and not really easy to use. For now, we haven't defined anything compositional, but the point is that we can. This game theoretic semantics is supported by compositional semantics that I won't show in details because it's revolve around hyperteams, and hyperteams are really hard to explain in 20-minute talks. But the point is, instead of focusing on strategies, we focus on plans. And plans are just sequence of actions. And why we use sequence of actions? It's because it's a linear object, a plan, instead of being a tree. And then it's easier to enforce realizability because we just have to look at one point instead of looking at one branch in some tree. And we still have the property that if each player has a plan, then it defines a unique play. So we can use almost the same logic, the same syntax as a strategy logic, but in an easier way. And when we have only one goal, quantifying over a tree or quantifying over just a sequence and enforcing realizability is the same. We really have a correspondence, a one-to-one correspondence between the two fragments of one goal and on plan logic and on strategy logic. But what happens when we have multiple goals? It's not that easy. Instead of having our trees, now we have just a simple sequence. And if we have multiple goals, it means that maybe the strategy for the shuttle will have to respond to the strategy of the car 1 and the strategy of the car 2. And this is not easy to do at once because if strategy of the car 1 and strategy of the car 2 are not the same, it means that the game will change, but we still need to choose only one action, which does not really correspond to what we wanted to formalize. And though, what we do is we add a new quantifier with strategy of the second strategy of the shuttle. And now the strategy of the shuttle 1 respond to the strategy of the car 1 and the strategy of the shuttle 2 respond to the strategy of the car 2. But now we also have a problem because they must be coherent in some way. If the two strategies of the car are the same, the strategy of the shuttle should answer the same. And what we do is we exactly define the property on variables that they are tied if they respond similarly. And we have a formal definition of this idea of similarity in that way. And now, when we have multiple strategies that are tied, those emulate one strategy in some sense. I will go really quick on the syntax and semantics. The syntax is almost the same as the strategy logic, just we have those two tyings operators that are almost modalities. And the semantics is given with hyperteam. And we have proven them equivalent to the game theoretic semantics. We can answer some model checking problems. So for the conjunctive and disjunctive fragments, and we have two exponential procedure because the construction of the game is not that costly. The translation of the formula is polynomial, and the strategy logic one goal model checking is already to explain complete, and we need to use it, so we have a to explain procedure. The to explain is on the side of the formula because the um, the game, once we fix the formula, so we fix the number of goal, everything is polynomial, right? So with church synthesis, we have the completeness of to explain. In conclusion, I've shown you a game theoretic semantics for realizability strategic reasoning. It's an alternative to the semantics of timeline for strategy logic. We have the operators that are in the game, that are players in the game, and we have a to explain complete model checking. Plain logic is a new logic that has compositional hyperteam semantics and allows for realizable Boolean calls. I haven't shown you, but the logic is completely well defined for the whole variety of combination of goals. What is left is to extend the construction of the game, so just the game theoretic semantics for fragments where we use both ends and or operators. We know which fragment we want to have because it's defined for strategy logic, but we don't have the full proof yet. And we want to compare maybe with what is missing when we have a conjunction of goals in strategy logic to have a to explain procedure is not really clear to me. So I want to look also a little bit at that. Thank you for listening, and I hope you have some questions.
Do you have any questions? Can I say something about what you mean by compositionality?
Compositionality means, yeah, I haven't defined it. It's just the definition of the semantics is given in terms of the semantics of the subformulas. So when you have a conjunction of formulas, you only look, for instance here, you only look at the semantics of this one, the semantics of this one, and then you compose. On this presentation, precisely, it's on the quantifier side that it's important because the semantics of plain logic will tell you what to do with one existential quantifier and the subformula, and that's all. And then you can compose them in order to have the semantics for the whole quantifier prefix. And this is really useful for the proofs. But as if you remember, when you have a scolem function, you need to hit the whole quantifier prefix at once. And this is why it's not compositional. Did I answer the question?
Sure. Just one question. So, Jenkins essentially so,
Sorry, I haven't been able to answer correctly to understand correctly the question. It was a bit noisy.
So, so with the brand or
I really just hear noises. I don't know if it's maybe I don't know if in the room you can hear the sound of the mic, but I can hear no words. Sorry.
No, can you hear me?
Yes.
Yeah, so I just wanted to understand better the difference between a strategy and the plan. When the strategy is not history dependent, does it coincide with the plan, or what else? What else is a plan?
Almost the plan in a way is a strategy that only depends on the step.
Okay, so it's not history dependent. Okay, fine. So
Yeah.
that's my question. Thank you.
But wow. Maybe I don't know.
I see. Hello, can you hear me?
Yes, I can hear you.
Okay. I wanted to ask, so what is the problem with, okay, I don't completely understand the problem with multiple goals and how tying as to tying them together solves that, and what exactly does tying entail in terms of having multiple goals and separate shuttles with separate strategies? Didn't completely understand that.
Yeah, I went a bit quick on that because I wanted to have time for questions. So the point is, when you have a strategy here, you can say that the strategy of the car says to turn right at some point, and the strategy of the car 2 says to turn left. It means that there is a difference between the two strategies, and the strategy of the shuttle can react to that because it will enter in different positions in the game. And so the strategy of the shuttle can say, against this history, I do that, but against this different strategy, I do something else. When we have plans, there is a problem because here, the strategy of the car 1 will say, I want to go left. The strategy of the car 2 says, I want to go right. The shuttle knows those differences. And so the shuttle, maybe to avoid collision, needs to go right, but in order to respect traffic protocol, needs to go left. And the question is, which action should I choose at this point in time? I have to choose only one action. I cannot tell exactly which one to choose. And this is why we add a new strategy for the shuttle that will be able to make the difference. So we will have strategy for the shuttle 1 that will respond to strategy of the car 1. So if the shuttle had to go right, then it goes right at this point. And the strategy for the shuttle 2 will go left in order to respect traffic protocol. The problem is when we do this trick in order to be able to answer to each goal, is that we lose completely the fact that those two quantified strategies should correspond to the same behavior in the game in a way. Okay, so we want to recompose strategies in some sense, if you will. And so because now they are completely different variables, they could decide, for instance, right from the beginning to choose a different action. And we don't want that. We want those two variables to represent one behavior. And in particular, in the initial position, the strategy should always choose the same action because the history is just the initial position. So you just have one action to choose. And this is exactly the idea of tyings. So when you tie two variables, you say that the plans that they contain must have the same action as long as when they are used in bindings, the history that is computed through these bindings is the same. So in particular, the smallest history that is just the initial position means that the first action of each binding variables must be always the same, for instance. Did I answer the question?
Yes, that helped. Thank you.
Thank you very much.
Thank you for waking up early and doing this talk, and move to the second talk.
Thank you very much.
That I can speak. Okay. Mhm. Yes, thank you.
And the second talk, the last one in the session is by Fury of Hansel, and it will be on two views on unification.
So I don't need to use this microphone. Okay. So thank you very much. It's indeed a pleasure to be here. And I really congratulate the organizers of this conference. So this is the first slide of my talk. And as you can see at the bottom, I just put the answer to a standard puzzle that you can find on the maths puzzles on the Guardian, which is the countdown equation for the year. So there will be one, I presume, also for in the first Monday of the new year, and so you can exercise and try to win the competition. Of course, you have to be very sort of witty for winning the competition. This is a very, very simple solution. So how do I move forward? We're here. Okay, so some of you might know that I enjoy too much mathematics, so at some point I thought that I should expiate all this enjoyment, and so I went into politics. So I'm a politician, so people often ask me whether being a mathematician or a computer scientist is actually useful in being a politician. So here is a classical example where indeed I believe it is mathematicians and computer scientists can contribute to a better politics, and it involves the issue of inequity. So we had here in this case something like 1,000 million, which is not a billion, but it is 1,000 million, because a billion, I think in English, is a million. So 1,000 million more euros with the revenues. And so how should we use it? And I said, well, let's see why did we have all this higher increase in the revenues? And this was due to VAT. And then so I asked, but how much of this was due just to inflation? See, VAT is an indirect tax. It is a sort of a flat tax. Poor people and rich people pay the same percentage. And moreover, with inflation, again, it affects the underprivileged classes. So I said, being a logician, I said, so how much of this 1,000 million actually comes from the inflation of the on the VAT? I computed, so I asked, because I am a logician, I asked the question, and because I am a computer scientist, I was capable of computing it. It was 200 million euros, and so you see, the moral is the cost of bread increases because of inflation. The government gets richer. So what should it do with this money? And of course, it should use it to reduce inequality. But this is another issue. Adding incentives normally increase inequalities. Remember this, because say the incentive to put solar panels, you can give this incentive only to people who already own a house. Because if you don't own a roof, and if you own a house at the end of the incentive, you are even better off because you pay even the electricity less. I can go on and on with electric cars and all this. So this is politics. Oh, now this is my. Can I get rid of? Otherwise, the title. Can I get rid of this? Okay, great. So this is my CV at the conference. So my first talk was in 1988. I had a paper with Rod Burstall, so quite some time ago. And then in Ahmedabad in 2018, and now this, and I am always very, very happy. This is something very pleased when I have the opportunity to visit India. And because I don't know how many of you are familiar with this, but really for me, when I first discovered Panini and the Ashtadhyayi, for me it was indeed a revelation. And seeing how the first example of beta reduction, you see, I'm in lambda calculus, appears in Ashtadhyayi in various forms, always got me particularly excited. And of course, this is something. Okay, now this talk is fundamental, very, very simple, and the reason why I think it's interesting is because it explains a very momentous change in logic when Jean-Yves Girard introduced with linear logic what was called geometry of interaction. And I tried to explain this geometry of interaction in more traditional terms. I will go back to that. And here is some fallout from that kind of research. And it is a different way of describing what unification is. I presume all of you know what unification, so it's a very fundamental talk. Please, how much time do I have? 20 more minutes. Okay. So here are two terms, sigma and tau. I write them in this form because this is the constructor in infix form, okay? And of course we normally view them as trees. But we can also focus on paths. Like here, what is the path for this gamma? It is left-right gamma. First you go on the left, then you go on the right, and then gamma. Now, a classical result, it's called pons asinorum, the bridge of the donkeys. You know, this is the way the logicians in the medieval times in Europe used to call the most basic facts. And so terms can be represented uniquely by the set of their paths, because no path leading to a variable at the end can be an initial segment of another path leading to a variable. Okay, so we can view them also as collection of paths. And now here is another approach. We can view terms as strategies. In the sense that, you see, if we go back to this situation where, of course, you have a beta here and a beta here, a gamma here and a gamma there, so we can pair the paths leading to beta and the paths leading to gamma, and here we have essentially this, that we can represent the term also as pairs of paths that lead to the same variable. Now, this, in fact, is a strategy. That is, if someone tells you, makes this move, you can respond with the second component, and on and on. And so this is how you introduce the game theoretic flavor in terms. And essentially the unification, just to anticipate, will be two terms unify if a certain number of games, certain kinds of games actually terminate. So of course, if a set of paths is compatible if no prefix of any path is an initial segment of another path. These are more, I call a variable which appears only once because, of course, because of this strategy, at first I have to reason on variables which occur at least twice. Otherwise, I don't have the counter move. But then, of course, one can also deal with terms that have also variables which appear only once. And I call such variables which appear only once, also the hapax variables. I don't know if you are experienced with philology, but hapax is a term in a text which appears only once. And so it's very, very difficult for those who study the document. You know, like the famous examples are the color of the sea in the Odyssey, in the Iliad and Odyssey, which is it's the color of the sea can be either red. It's the color of the wine. Now, can you imagine the color of wine being the color of the sea? But of course, we don't really know because it appears only once. So what exactly Homer called, what was the image that Homer had in mind when he described the color of the sea because of this hapax occurring only once? It's still matter of debate among philologists. So hapax variables for the time being are left there. So I hope that now when you see a set, you think about the set of paths. When you see a term, you can think about the set of paths, and you can reconstruct the term, or you can see it as a potential strategy. And I'll tell you what the game is. So the two views of unification, one is the standard one. You have a substitution for the variables, which makes the two terms equal. And the other one is we take the two games and make them play against each other. And essentially, we can simulate each move in the game deriving from the type sigma by a composition, iterated composition of moves by the strategy R tau. Of course, this can be iterated many, many times, but after a number of plays, you can simulate all the moves in the representation of sigma and all the moves in the representation of tau in this pattern. And this is the alternate definition of unification. And I could just finish my talk here, only that I will show you the connections with the geometry of interaction. It's quite, I think, interesting that you can describe unification in this way, and I give also some other comments. So here is an example of the game. So I want to simulate the term that this L alpha left alpha, right alpha. Okay, so this is just a way of describing this very, very simple term. So what I do, I say, well, but of course I can replace alpha with L beta here, and then I can make a move in the game tau, and I come here. But then this is essentially an instance of this. So I can move now again in the game sigma. But this is an instance of that. And of that. And once I'm here, now I can make a move in tau. And then I can come back. And once I come back here, I have precisely arrived at what was a move, or actually an instance of a move in the original game. And this I can do for all situations. I can simulate this in different ways, because of course LA can be an instance also of LR gamma. Here it was an instance of LL beta, and now it is an instance of LR gamma. And again, also in this case, I can go here. The red arrows are instances, and the blue arrows are, in fact, moves in this game. So 4, 5, 6, 7, back. So I have reached. Well, of course, the two terms unify, and so there is no problem. If the game does not terminate, or you can prove that it does not terminate, then of course the two terms do not unify. Now you can do the same with beta. You start from here and you go move all around. As you see, I am not doing it top down. I'm doing it bottom up. I'm only looking at the variables, the paths, and the moves. So in this case, I have a different pattern, and this is for the last one. So I have checked that the two terms unify without actually going through the traditional approach. Now, how can I extract the substitution? Well, I can, if you go back, you can see that I have simulated this move in sigma by this move here in, sorry, this move in tau by this move here in sigma. And previously I had simulated this move in sigma with this move here in tau. So for each of the moves in the first term, I can find paths in the second. And so I have a collection of paths. And as I told you, from a collection of paths, you can reconstruct a term. And that is precisely the substitution that I obtain. So by just looking at the paths that I have in this game, I have achieved the production of the substitution. Of course, all this needs to be generalized, and here we have terms in the general form. I don't really want to go into the details, but I presume that this is not particularly, it's obvious. And of course, as I told you, from trees, I can go back, I can go to collections of paths, and from collections of paths, I can go to trees. This was sort of, I presume, quite intuitive, but of course, it has to be formalized properly. Now here, this is the traditional, okay, so the traditional, so I said in the title of the talk is two perspectives on unification. The traditional one is the one a la Robinson, and you go top down. Okay, here is just an algorithm. From from complex formula, you sort of go to simpler formulas. You have to make at some stage a replacement, but essentially you move top down. While when we take this approach, we are, as I'm saying, doing it bottom up. Again, in the paper you find the complete formal definitions, which here I have just listed. And now we come to Girard's geometry of interaction and see how the two things, how one thing inspires the other, or vice versa. You know, Jean-Yves Girard, you might know, Jean-Yves Girard is this French logician who really made an extraordinary impact on the logics community when he introduced linear logic, which was a resource-sensitive logic. It was an analysis of first-order logic. And he came up with this rather elaborate semantics, which is called geometry of interaction. And so geometry of interaction is a general program originated in which aims at giving language-independent mathematical models of algorithms. So he introduced it for lambda calculus and for linear logic. And the present paper provides, so to speak, so in Sanskrit one should say Eva, I don't know, I mean, how familiar you are with Sanskrit. But, it seems, you know, Eva is often used to say, it seems, the geometry of interaction of unification. In a paper that is appearing on mathematical structures of computer science, we have in fact explained that the basic notion in geometry of interaction of linear application between functions amounts essentially to the resolution doing in this paper is sort of the opposite direction. We are explaining here. In this paper we explained geometry of interaction in terms of resolution, and here we are explaining resolution in terms of geometry of interaction. This is more technical stuff, which probably we don't want to know, but just you might be interested in knowing that it exists in the paper. So it's just all this is formalized. I just want to reach quickly, the definition of the very formal definition of the geometry of interaction, you see, is this, that we can simulate the strategy R tau by just sort of, and this is the flow of diagram, the flow of control diagram, by just sort of iterating moves in this game and coming out with the final outcome. So if you want to simulate a move in R tau, you give the initial move here, then you keep playing this game, and you come out with the other the second component of the strategy in R tau. And the same is with inverted roles. We have to check first that you can simulate a sigma in tau, and then that you can simulate tau and sigma. And essentially, if you think about paths, you are sort of producing for every pair of paths in tau, you are through this process producing, simulating pairs of paths, mediating through sigma. So each time you have an odd sequence of moves, and if you want to simulate a move in tau, then this is an odd sequence of moves that start in sigma and end in sigma. This is up to relations up to substitution, because the final variable in the path has to be sometimes replaced. There are lemmas which sort of formalize what I have explained awkwardly with my hands. And here is the main result. So the standard unification is the same as this unification a la geometry of interaction. Hint of the proof: we establish a series of invariance lemmata, which decompose the complexity of the terms and then rebuild this complexity. And at the bottom, the two terms are so similar that it is obvious by just on the nose it holds that the two notions of unifications coincide. This is, of course, the technical results that are in the paper that I'm not interested in showing. So here at the end, I have to explain how to model constants, how to model Hapax variables, and how to model terms which have variables in common. And let me see. So I said unification and resolution. So what is the relationship between unification and resolution? Well, in this case, you see, if I want to resolution and unification have this relationship normally, that you find if you want to make a resolution of sigma one arrow sigma 2 and tau, you simply unify these two terms. You add a new variable. Of course, I cannot do that. We cannot do that here because we need to have strategies. So you simply duplicate it, but it doesn't matter. And that provides the connection with resolution. In fact, this is the definition of the linear application in Abramsky or Gerard's geometry of interaction. And and in fact, the person who phrased it using games was essentially Abramsky and Hyland in something like 20 years ago. But the original formula was expressed using linear operators in C-star algebras. But again, it's basically the same because Girard used C-star algebras. But all that machinery, in a sense, is not really necessary if you view what they're doing, as we have shown, simply as unification. And of course, you can have also, once you have realized this, also multiple unification and all the universe of potential generalizations, if you want to look at it on the side of the calculi, on multi-valued calculi. So with a forward, I don't know, that's normally people say, I don't know, besides if my journey was so long that often when I give a talk, I write my birthday and also my expected death date. Which is something that medieval mathematicians used to enjoy playing with, writing, computing the date of their death. Mine is currently is the 14th of January 2045, but I didn't write that, so I've still got some time. Okay, so that's it.
Thanks for a great talk. One of the things about the Robinson algorithm is that it gives fixed points. It's very based on fixed points. And I'm trying to see what the bottom-up approach you've taken gives us there. And the other thing is that one of these quests for the Holy Grail is looking for a linear time unification algorithm. The Martinelli-Montanari is great at parallelizing things, but the quest for the linear time unification algorithm is still very elusive. It's not even clear whether it does not exist or something. Any comments on this? Can this tracing paths give you any insight?
Well, thank you very much for the question. Of course, it's both are very interesting. I think that the answer to the first question is that also here there's an iteration. In fact, and really it is a fixed point that we reach, and the two terms unify precisely when there is a fixed point. And Girard also, for his linear application, uses the execution formula. And so it is a matter of convergence to this fixed point, because you iterate and you have to get back to, so the fixed point is you reach the other path, if there were two paths. Now, as far as the complexity of the algorithm, I'm afraid that this, it can, since there is a change in the perspective, it can produce some insight, but as it appears, you see, when it succeeds, things are, I would say, rather proving that two things do not unify. That I think is more complicated, because you have essentially to show that there is a move that you cannot simulate, and that it can be very, very expensive, in fact, because this is a criterion.
If that unification is bidirectional, is it simulate or bisimulate?
It is a bisimulation here, but the bisimulation is normally defined intrinsically. This first you simulate here and then you simulate there. So I wouldn't call it a bisimulation. It's a double simulation. Thank you. Okay, thank you. But because I have to give you back this.
lady here.
Escape press చేస్తే మీకు ఏమేం కావాలి?